So here is the main message of the paper. So it's well known that the dynamic games with private monitoring lack recursive structure in some sense. I'll be more specific about what it means, but basically it implies that characterizing equilibrium payoff set is hard. But nonetheless, in this paper, we identify a sufficient condition with which we can characterize the equilibrium payoff set that can arise for some monitoring structure with a fixed discount factor. So the quantifier is that from this characterized equilibrium payoff set, if we pick a payoff profile, we can at least find one monitoring structure with which that payoff profile is an equilibrium payoff. Okay, so that's the quantifier. And the important point of this paper is that we fix the discount factor and fix utility functions. So the restrictions on the equilibrium payoff set actually come from utility functions and the discounting, while many other papers get restrictions coming from monitoring structure but taking discount factor going to 1. Okay, so we are sort of looking at a very different questions. So for us, the important point is that we want to fix the discount factor. But the cost that we need to pay is that since we don't have a recursive structure, we need to look at some Redux problem. Basically, we cannot fix the monitoring structure. Okay, so that's the trade-off. And so the main message is that we sort of want to provide a falsifiable theory of the repeated games. And one way to do it is to fix the utility function and the discount factor and say that this is the set of equilibrium payoffs that can arise for some monitoring structure. So we can say that something outside of that set cannot happen on equilibrium, no matter what the monitoring structure is. Okay, so that's what we are trying to do. Okay. So we first specify the model, and then we give you an upper bound of equilibrium payoff set. And basically about this equilibrium payoff set, we will derive 4 main results, one of which says that this one upper bound is actually a characterization of equilibrium payoff set with some monitoring structure. Okay? So that's that. And so the model is basically a 2-player game. We will talk about the case with more than 2 players if we have time in the end, but most likely not. And the set of actions is finite and denoted by capital set AI. General element is small set AI. And a set of private signals that the player I can observe is a capital set Yi, and the general element is small yi. And for each player I, we can fix ex ante utility function coming from some action profile A. So this is utilities that the player I gets if players play action profile A. And given the history, so this is what happened in period 1, or like what actions were taken in period 1, what signals were observed in period 1, etc., up to the previous period. And in period T, this action profile is taken. Then the conditional distribution of the signal profile of period 1 is determined by some conditional distribution function Q of T of this signal profile Yt given this entire history. So this monitoring structure is not necessarily repetitive or stationary, but could be history dependent. Okay? And we denote the, we use Q star to denote the set of all the monitoring structure. So Q star contains any kind of history dependent monitoring structure. Okay? And specifically, when we want to consider a particular monitoring structure which is repetitive, which means that the distribution of signals in period T is sort of stationary and depends only on today's action, then we say that this monitoring structure is repetitive, and we use this Q of repetitive, like RE, to denote the set of all the repetitive monitoring structure. Okay? So when we talk about a general monitoring structure, we use Q star, But sometimes we want to ask, well, but this monitoring structure seems too general. So can we get more restriction by assuming that monitoring is repetitive? Then we can talk about this object. Okay? And discount factor is assumed to be common and less than 1. And so this is a model. Okay? Questions?
So
yeah.
Q star depends on T?
Q star can depend on T, yeah. Okay? So apart from this history dependence, this is a fairly standard model of private monitoring, I would say. Okay? So the ultimate goal that we would love to obtain is to characterize a set of equilibria with a fixed monitoring structure and fixed discount factor. But this is too difficult, at least for me and Alex, unfortunately. So our attempt is to answer the following question. So first, fix a stage game and the discount factor. And suppose that the outside researcher does not know the signal structure among the players. So this is sort of a robust prediction about the monitoring structure. Then what can we say about the set of possible equilibrium payoffs? And so specifically, E of Q delta is the set of equilibrium payoff given monitoring structure Q and discount factor delta. And if we take a union of this set with respect to all possible monitoring structure, then this is basically the answer to this question, right? Because we do not know what is a monitoring structure, so we know that the Q is included in Q star, but we don't know nothing else. But then, what is a possible set of equilibrium payoffs? Okay? So that's what we are trying to answer. Yeah? Then to characterize this object, what we do is to first find the best monitoring structure, because we don't want to talk about the set of the monitoring structure all the time. So if we can find the best monitoring structure, which gives us the largest equilibrium payoff set, and we can characterize the equilibrium payoff set under that monitoring structure, then we are done. Okay? So the question is whether such a best monitoring structure exists, and if it exists, can we characterize the equilibrium payoff set with that monitoring structure? And here is the answer to the first question. Yes, there exists the monitoring structure, and which we call omniscient mediator. So let me explain what it means. So in each period, game proceeds as follows. So here, it's not exactly the monitoring structure in a defined game, but we actually allow players to have an access to the mediator. So this is sort of a modified game. So the players are like usual players plus mediator. And what the mediator does is that given her history, so what the mediator does is that by revelation principle, she observes action profiles. So we assume that the mediator can observe everything and makes a recommendation to each player. So this is the mediator's history, which consists of action profiles and recommendation profiles so far. As a mediator recommends some action profile according to some some distribution of action profiles. And what each player can observe is the following. So we assume that the player I can only observe her own action and her own recommendation and take some action. And by revelation principle, we can say without loss of generality, at least on the equilibrium path, the recommended action is taken by the players. Okay? Then, since players do not know anything but what she can hear from the mediator, her incentive compatibility constraint is the most relaxed form, while the mediator can observe everything. So this mediator is super powerful in that sense. So that's what it says. So the mediator observes everything, while player I can only observe her own recommendation and action AI. So basically, by investigation and revelation principle, we can say that anything that we can do with some monitoring structure can be done by this omniscient mediator. And since we allow the monitoring to be history dependent, basically we can consider the signal distribution which mimic what mediator does in this game. So what we can do with this mediator can be done with that history-dependent monitoring. So basically, we establish this equality. So what we have to do now is to characterize this set. That's the answer to the first question. Questions? So basically, here we see the mediator as a player who picks mu star. So that's mu t. That's why we don't have a union of mu t. But you are right that if we fix the behavior of the mediator, what we need to have here in front of this set is union of all mu t. And this equilibrium payoff set depends on mu t. Then the answer to the second question, can we characterize this set, is, I mean, we probably can, but it's very hard. And at least it's almost impossible to get a clean characterization. Why? Because there is no recursive structure in this game in a sense that the continuation strategy is not necessarily a Nash equilibrium of the original game. The reason why is that, from the beginning of the game, each player's information set is just singleton. Everybody knows that. But after first period, player 1 knows what action he took and what recommendation he received, but he doesn't know what action was taken by player 2 or what recommendation was received by player 2 and vice versa. So player 1's information set connect this one and this one because these two sets only differs in player 2's information, and this is another information set of player 1, and this is information set of player 2, and this is information set for player 2 as well. And as you can imagine, if we keep writing the game tree, then the structure of the information sets gets more and more complicated. And so the incentive compatibility constraints that the mediator needs to satisfy has a very ugly form to write down as a constraint. Okay? So one way to sidestep this issue is that suppose now that not only player I observes her own action, but also observe the entire action profile, then at least on equilibrium path, we can recover the common knowledge of the past history. Because on equilibrium, everybody follows the recommendation. So we can at least recover the on-path common knowledge. So let's write down E of delta be the equilibrium payoff set with mediated parameter monitoring. And again, as I answer to the Roger's question, this E incorporates mediator's strategy already. Okay? And then this E of delta is easier to characterize compared to E of delta Q star because we can recover on-path common knowledge. But the bad news is that this guy is too small to work as an upper bound of the equilibrium payoffs. Okay, so E of delta does not always include E of delta Q star, but we identify a sufficient condition with which the Pareto frontier of E of delta Pareto dominates, or weakly Pareto dominates, because this guy is at least weakly better than this, right? So weakly Pareto dominates the Pareto frontier of the equilibrium payoff set with omniscient mediator. So in other words, as long as this sufficient condition is satisfied, this set can work as an upper bound. Okay? And then we may wonder, the fact that this guy is too big is probably because we allow history-dependent monitoring. So suppose that you say, well, but we only care about the upper bound for the repetitive monitoring, private monitoring. The answer is still no, in a sense that we can construct unmediated and repetitive private monitoring such that that monitoring structure outperforms mediated perfect monitoring. In other words, it means that the set of mediated perfect monitoring does not always include the set of equilibrium payoffs with repetitive private monitoring either. Okay, so even if you only care about repetitive monitoring, this set is not always working. And the second one is, as I mentioned, we can offer sufficient condition to ensure that mediated perfect monitoring is the best monitoring structure, and then offer recursive characterization of the equilibrium payoff set with this perfect monitoring, and with this sufficient condition, this characterized set works as an upper bound of the equilibrium payoffs. And then another question is that how tight is this bound is? And it's tight in a sense that there exists a repetitive private monitoring which achieves this set at least as a correlated equilibrium. Okay, so for Nash, not entirely sure yet. So here is the plan, and of course we don't have enough time to go through all of them in the detailed way. So our plan is to spend some time in the first one and spend some time in the first one and some time in the second one, and the other parts, I guess I have to ask you to read the paper if you are interested. Okay. All right. So the first one, if you attended site conference at Stanford last summer, we already had a result about this first one. So probably like Jeff was listening to our talk probably last year. So this might be a repetitive for him, but let me go through this anyway, and stop me if you feel like I'm too fast. Okay. On equilibrium path with private monitoring. So here is the intuition why repetitive private monitoring can outperform mediated perfect monitoring. So at least on the equilibrium path, since everybody knows that everybody follows the recommendation, so the on-path history is common knowledge. So incentive compatibility constraint needs to be satisfied after history by history. Okay? While with private monitoring, since you do not know what action was taken by the other players or what signals are observed by the other players, again, your information set connects a bunch of histories, and incentive compatibility constraint for each player needs to be satisfied only on average within each information set of each player. So if we just count numbers, sometimes the number of constraints that we need to satisfy here is much smaller than the number of constraints that we need to satisfy with perfect monitoring. That's the rough intuition. And using this observation, we can come up with a game such that there exists a set of equilibrium payoffs from repetitive private monitoring such that summation of player 1's equilibrium payoff and player 2's equilibrium payoff is greater than what we can achieve in the mediated perfect monitoring counterpart. And as I mentioned, the intuition is that there are three effects of private monitoring. One is that detection of deviations become harder with private monitoring because monitoring becomes imperfect. So that's a bad news to try to extend equilibrium payoffs. And also the second one is well-known effect, which means that we can create correlation by considering as correlated private signals. But this effect can be done by the mediator also. So this effect does not expand the equilibrium payoff set with with private monitoring if the counterpart is mediated perfect monitoring. Okay? And only the third effect can work to achieve this direction of the inequality, which is, as I mentioned, with private monitoring, we can bunch information set and sometimes relax incentive compatibility constraint. And this cannot be done with the mediator. Like as soon as players observe actions by perfect monitoring, they can see and they cannot forget what they can observe. So this result says that this third effect sometimes dominates the other two effects. Okay? Questions? No. How much time do I have? Like 40 minutes or so? 50. Okay. Then.
Could I just ask a question?
Yeah.
You could start opposite, right? I mean, in terms of the mediator, you could start in the situation saying that the mediator basically precludes any observations, maybe besides your own history, right? And then the mediator can sort of disclose more or less in some sense. And then the fact that bunching of information cannot be done by the mediator, that depends a little bit more on the definition of the mediator rather than
so I guess
the inherent nature of the problem.
I guess what you're suggesting is that there's an omniscient mediator problem where players don't observe past actions unless mediator discloses that. Then yes, we can sort of start from that. Then yes, we don't have the third effect. So surely the omniscient mediator's equilibrium payoff set is bigger than the equilibrium payoff set with any monitoring structure. Yeah, but I guess as I mentioned, if our goal is to characterize the equilibrium payoff set, that equilibrium payoff set with omniscient mediator is very hard to characterize. Very hard to characterize. Yeah, so.
It's an interesting, right? I mean, I would think it's an interesting problem.
Yeah, I agree that it's an interesting problem. Yeah.
So maybe we can chime in and just sort of repeat what Takua said, right? So you know, the goal here is we want to characterize the set of equilibrium pairs that can emerge for some private monitoring structure, or equivalently give an upper bound that we'll have for a particular private monitoring structure. Now, one thing that would be such an upper bound, like Takua said, is the equilibrium set with this omniscient mediator, where players only get their own recommendations and actions. But the problem is that in general, that set doesn't seem to have some kind of tractable characterization, at least not as far as we know. So what instead we're going to characterize is the equilibrium payoff set with perfect monitoring in a mediator, which is what we're looking at here. What Takua is showing now is that it turns out that sometimes that set is not an upper bound of what you can get with mediated perfect, with private monitoring. Sometimes there's private monitoring that does better than that. But so that's what we're showing now, and then we're going to show that on the other hand we have some simple sufficient condition under which examples like this can't happen, and actually that thing that we can characterize is also an upper bound.
Yeah. But I agree that if possible, directly characterizing what can be done with omniscient mediator directly is an interesting. So all the example can work for infinitely repeated games, but for simplicity, let's assume that there are only 2 periods. And 2 players, 2 period model that works for infinitely repeated games in a very straightforward way. And the discounting between period 1 and the period 2 is assumed to be a 6th. Okay, so it's a very high discount factor. And here is a game. This is 4x3 game. We are not entirely sure whether this is a minimum example in a sense that, can we construct an example with 2x2 and things like that? We are not entirely sure. But at least this works as an example. So here is a payoff matrix, and let's investigate what it means. So this 2-2 is the only cell where the sum of the players' payoffs is no less than 4. So this is basically what we want to achieve to get a higher summation of players' payoffs, and which requires player 1 taking action U. Okay? But no matter what player 2 is taking, player 1 can get deviation gain of 1 from U to D. So to incentivize player 1 to take U, we need to, and also the minimax payoff for player 1 is 0. If we just allow him to take B, then player 1 can ensure payoff of 0 by taking just B. So basically, player 1 can deviate from U to D, gets 1, and ensure him of getting 0 in period 2, which means that to incentivize player 1 to take U in period 1, period 2 action profile needs to be this one, because the discounting is 1/6. Okay? Then, if monitoring is perfect and player 2 observes that player 1 is taking U in period 1, then player 2 will think that, aha, okay, so here we are today, which means that we must go here tomorrow, but then I should deviate from here to here. So such an equilibrium does not exist. While if we consider some correlated mixed strategies in player 1 in private monitoring, we can actually support this 2-2 and going to 6-3 with some positive probability, which works into the direction to improve the summation of the payoffs. Okay, so let's see how it works. So here's a fairly straightforward explanation of why UL cannot be taken in period 1 with private monitoring and the mediation. Because suppose U is recommended to player 1 in period 1, then one can deviate to D and get 1 and ensure payoff of 0 by taking D in period 2. So that such a thing is not a profitable deviation given this very low discount factor, we need to go to TM, this 6 minus 3, after player 2 taking U. But with perfect monitoring, player 2 can observe period 1's on-pass recommendation, so player 2 wants to deviate after observing U. So that cannot be an equilibrium. Okay? And then here is a perfect monitoring example. So the signal structure is as follows. So player 1 does not observe anything. Player 2 observes two possible signals, M and R. And if player 1 takes U, then signal M happens with probability 1, while otherwise these two signals can happen with probability half and half. And assume for a moment that the players receive payoffs after the game is over. So there's no brief update observing the realized payoffs. We can relax this assumption, but just for simplicity. Okay? So basically, if you observe R, we can say that U is not taken. But if you observe M and the player 1 is mixing, we cannot tell whether U is taken or not. So here is a strategy profile. So for player 1, what she does is to take a mixed strategy and mixing U and D. And in period 2, if the previous action was U, then player 1 takes T. Otherwise, she takes B. So here is a summary. And for player 2, first take L. And in period 2, take M, capital M if small m, this is a signal, is observed. And take R, capital R, if small r, this is a signal, is observed. So basically, this signal is sort of a recommendation for player 2. Okay? And then we can check optimality of each player's actions at each history. But let's look at player 2's optimality in period 2 because this was a problem with perfect monitoring. Okay? So after observing M, player 2 believes that player 1 took U with probability half. Why? Because if player 1 took U, then player 2 observes M for sure. Otherwise, M and R happens half and half probability. And these are player 1's mixture, so this is just a base roll. Okay? And after R, player 2 knows that the player 1 took D. So after M, player 2 believes that the player 1 took T and B half and half. This is her belief. So half and half. So L gives her 0, M gives her 0, R gives her 0 as well. So everything is, she's indifferent among every action. So actually the equilibrium action is optimal. After R, she knows that the player 1 took D, and after that, player 1 will take B. So given that, taking R is the best response. Okay? And you may think that here is a lot of indifferences and things, but we can break the tie, actually. So we can also verify player 1's incentive in each period and the player 2's incentive in period 1. And importantly, if player 1 took U, then player 1 will take T, and player 2 will observe M for sure and take M for sure. So Tm will be realized. So after this will happen as we have seen from the beginning. And so player 1's incentive in period 1 is satisfied, and in period 2 it's just a best response. And the player 2's incentive in period 1 is also satisfied. And then we can say that with perfect monitoring, U cannot be taken. So in each period, the summation of action profile, which is denoted by Vt, is no more than 3 by just looking at the payoff matrix. But in private monitoring, since this profile can be taken with some positive probability in period 1, we can actually achieve better summation of the payoffs compared to mediated perfect monitoring. And yes, here's the robustness check. So this is robust to a perturbation of payoffs. So this does not depend on weird indifference in incentives. We can also create a similar example with private strategies in public monitoring also. So focusing on public monitoring doesn't help much. And we can also allow players to observe their own realized payoffs after each period and update the beliefs based on the observation. That can be done as well. So this is basically shows that there's a robust example saying that mediated perfect monitoring is not an upper bound of the repetitive private monitoring. Yes. Good. So here is basically the first point. And the second point is that we offer a sufficient condition to ensure that mediated perfect monitoring is the best monitoring structure. And to give you the sufficient condition, I have to ask you to walk through a couple of definitions. These are not super complicated, I hope. The first one is a maximum deviation gain. So suppose that you know that which action profile is recommended by the mediator, and you can deviate to maximize your payoff, then this is a maximum deviation gain. And if suppose that a deviator believes that she will be minimax forever after deviation, this needs to be sequentially rational, but forget about that restriction. Then, given this belief, if player I gets a continuation payoff no less than W lower by I, which is characterized in this equation implicitly, then player I does not want to deviate from any recommendation. And the reason is that in this characterization, this side is one-shot maximum deviation gain. And this side is that given this belief that the deviator will be minimax forever, this is a continuation payoff after deviation. This is an on-pass continuation payoff. So this basically means that the on-pass continuation payoff is sufficiently high. And the sufficient condition is basically says that this minimum continuation payoff is sufficiently low in a sense that it doesn't overshoot the set of feasible payoffs. So let me formalize that argument. And given W lower bar, we can consider the set of payoff profiles where player I gets this W lower bar I. So as long as continuation payoff is in this set, player I does not have an incentive to deviate. That's the intuition. And U of A is the convex hull of a feasible payoff set. And the main theorem of this paper is to say that if set of feasible payoffs, the set of continuation payoffs where player 1 does not want to deviate, and that where player 2 does not want to deviate, has a non-empty relative interior. Relative means that a relative in a space that is spanned by feasible payoffs, then mediated perfect monitoring achieves the highest private frontier. Okay? So the picture-wise, so the set of feasible payoffs is here. And W1 means that as long as continuation payoff is here, player 1 does not want to deviate. And the set W2 is the set that as long as continuation payoff is here, player 2 does not want to deviate. And if this set is non-empty, then we are fine. And in the previous example, since discount factor is too low, after U is recommended, player 1's set is very, very high. And then the intersection with the continuation payoff where player 2 does not want to deviate is not intersect with the feasible payoffs. Okay, so this does not give us a super high discount factor in terms as a restriction, because these two sets depends on the discount factor. Why? Because as Bev mentioned, this the definition of W lower bar I depends on delta. And as delta going to 1, this side is getting 0. So W lower bar is getting closer and closer to the minimax payoff. So basically, this set becomes non-empty with respect to the relative interior for sure for the high discount factor. And how high the discount factor should be, it's not super high. We call that it's moderately high. This is just a subjective judgment. But for example, in this usual prisoner's dilemma, the discount factor needs to be greater than half to satisfy this condition. Okay. So then the equivalent statement is that since we are looking at the palette frontier with 2 players, we can look at the palette weight lambda, and we want to maximize the score, which is a palette weighted sum of the utilities. This is a mediated perfect monitoring. This is omniscient mediator, where mediator observes everything and players don't observe anything. And this one gives us at least weakly higher score than this one. So the set looks like this. But of course, this set includes everything. So basically, the true picture is that the palette frontier of the perfect monitoring is equal to the palette frontier of the omniscient mediator. That's what we get, basically. Okay, so there are 2 steps in the proof to show this inequality. The first one is to show that this intersection of UA and W1 and W2, this is actually included in this mediated perfect monitoring equilibrium payoff set. Okay? So that's the first step. And the second step is to consider what we can achieve by the omniscient mediator outside of this set, because this set is already proven to be included in this set in the step 1. So we are left to show that this set is also outperformed by mediated perfect monitoring. Step 2 is more complicated, so we may skip this unless time permits. And the step 1 is kind of like straightforward, but it's a little bit surprising in a sense that the proof is very simple, but we didn't expect it at the beginning. So take any V from the relative interior of this set. So this is a picture. And since V is interior relative to the set of feasible payoffs, there exists a fully mixed strategy of the mediator, the stationary strategy, that achieves this payoff profile as an equilibrium if this mu is repeatedly recommended by the mediator. Okay? Then suppose that the mediator has follows the following automaton strategies with 3 states, regular and punishment for each player. And start with a regular state, recommend this mu. As long as nobody deviates, stay here. Remember that the mediator can observe everything. And if some player I unilaterally deviates, we go to this punishment state where best response and the minimax I is recommended forever afterwards. Okay? Then the natural question is that why such a thing is sequentially rational, because we are looking at the sequential equilibrium. So incentive compatibility after player I herself has not yet deviated can be proven as follows. So since the on-path recommendation has full support, remember that we took this mu so that this recommendation has a fully mixed strategy. So everything can happen on equilibrium path, meaning that unless you yourself has deviated, you believe that they are in state regular, which means that they believe that the continuation payoff will be Vi. And we take this V from the set where continuation payoff is sufficiently high so that the player I does not want to deviate. So given that the player I will be minimax after her deviation, which she will be after player i's deviation in this equilibrium construction. So you don't want to deviate. And if you yourself have deviated, you are here, and you cannot do anything, and you are recommended to take a best response. So this is a sequential equilibrium, or like this is sequentially rational to follow recommendation with respect to the following modification. So suppose that you yourself have deviated. You believe that best response minimax I should be recommended to you. And suppose that you found that you recommended something other than best response, or the other guy is taking a strategy which is outside of the support of the minimax strategy, then you find that we are not here. So we need to modify, but we can show that after such a history, only thing that is consistent is that you believe that you and the deviator, or you and the opponent deviated exactly at the same time, and so you are still in a regular state. So we can deal with that history as well. So what we have done so far is that this set is included in E of delta, and of course this is a feasible payoff set bound. So the omniscient mediator cannot achieve more than feasible payoff set. So for this set, this omniscient mediator and the mediator perfect monitoring coincide. Then we can sort of do more complicated exercise for other directions. So basically, yeah. Yeah, so W lower bar should be indexed by delta. And so basically this says that the W lower bar 2 is sufficiently high, and the W condition pair for player 1 is sufficiently high. And the sufficient condition basically says that this is non-empty.
The boundary view of A was also the boundary of what is feasible with perfect information. The intuition is that down there, if you punish, you would go back. The punishment part would go up into the zone where you have already covered.
So yes, so intuitively, it's better to, if punishment goes somewhere around here, it's better to go around here. Yeah, that's the intuition. Yeah. And related to Roger's question, actually, if you care about the fact that, we always achieve some part of the Pareto frontier of the feasible payoff set, as Alex says that it's not true for all the directions, but you probably want to get some bound that is globally away from the feasible payoff set sometimes. And there are other sufficient conditions such that we have some characterization of the set of actions which can be taken in equilibrium with omniscient mediator. And so let this support be denote this characterized feasible supportable actions with omniscient mediator, and we can replace all set of actions with this set of supportable actions and do the same exercise. Then sometimes, so this is the original definition of maximum deviation gain, sufficiently high continuation payoff, etc. And here is A and A, etc. We just replace these by support, but still allows you to deviate to pretty much any actions and do the same exercise and say that if this thing is non-empty with A replaced with these supportable actions, then we can sometimes get bound globally away from the feasible payoff set. All right, then step 2, I'm not entirely sure how much detail we can go through, but basically I can go to the point that Actually, at least we can catch up with Roger's intuition to some extent. So the step 2 is to consider other directions. So given some recommendation schedule, which is a mediator, the mapping from mediator's history to the distribution of the recommendations to support some payoff V with this omniscient mediator, we construct an incentive compatible recommendation schedule to support some V tilde, which gives us a higher score with perfect monitoring. Okay, so this is what we will do. And without loss of generality, we can assume that the on-path recommendation has full support and that the deviator will be minimaxed forever by the similar trick as we support this set, because we can always mix the equilibrium path of going some part here and some part here and then like part out the recommendation slightly to make sure that the on-path recommendation has always full support, so that we can punish the deviator without notifying the mediator as before. And let's consider how to support this V equilibrium pairs where the palette weight, where this V is the maximum of the score, is sort of like a flatter than this boundary of the palette weight for this intersection of UA and the W1 and W2. And intuitively speaking, here, basically, we want to maximize player 1's payoff by sacrificing player 2's payoff a little bit, because palette weight is very high for player 1 and very low for player 2. Okay? So intuitively, player 2's incentive compatibility is likely to be binding if we want to push that direction. So first, we make sure that the player 2's incentive is okay by changing the recommendation as follows. So suppose that the mu-t is the distribution of the recommendation in this omniscient mediator. Then we can calculate the distribution of the recommendation of this recommendation schedule with the omniscient mediator only conditional on player 2's history. Okay? And then after each history of the mediator, instead of recommending the distribution of recommendation conditional on the entire history of the mediator, suppose that the mediator recommends recommendation according to the distribution only conditional on player 2's history. Okay? As long as mediator uses this recommendation schedule, player 2's incentive compatibility is satisfied with perfect monitoring if it is satisfied with omniscient mediator, because this is what she knew with the omniscient mediator as well. Okay? And then, as Roger mentioned, if the player 1's incentive compatibility constraint is not satisfied with, because we changed the recommendation distribution slightly, so player 2's incentive is okay, but the player 1's incentive might be violated. And the only case where player 1's incentive compatibility constraint is violated is that her continuation payoff is below this the continuation payoff that guarantees player 1's incentive compatibility constraint by definition. So the continuation payoff after which player 1's incentive compatibility constraint is problematic is here and there. And then it's better to use this point rather than this point in order to maximize the ex ante payoffs, as Roger mentioned, basically. And the last thing that we need to care about is that here, after some history, we decrease player 2's continuation payoff. So suppose that this happens in period 2, then player 2 in period 1, looking ahead that, well, after some history, my continuation payoff might be decreased. So then now I want to deviate. And if such a thing happens, we need to increase player 2's equilibrium payoffs to exactly cancel out the effect of this decline of the player 2's continuation payoff. And basically, we can do that using the convexity of the equilibrium payoffs, basically. But I think I will not have time to cover this. And so that's basically what we do. So basically the summary is we start with a recommendation with which player 2's incentive compatibility constraint is satisfied. And then we push player 1's contention payoff so that it is always like here, so that the player 1's incentive compatibility constraint is satisfied. This may reduce player 2's contention payoff. So make sure that the player 2's contention payoff is no less than the original equilibrium payoff by again manipulating the contention payoff location slightly. Okay, then that's completes the proof. So if we go back to the original place where we are, so basically we are finishing explaining that why this sufficient condition ensures that the mediated perfect monitoring is the best monitoring structure. Okay? And very quickly, we explain what recursive characterization we can obtain. So the characterization is the same as Abri-Pierce-Stachetti operator or Shapley operator, except that the optimal penal code is replaced with the minimax, minimaxing the deviator forever using the same trick as we supported this intersection by using this kind of trick, mixing on-pass recommendation slightly so that we can punish the deviator without notifying the punisher, basically. Okay? So then, and also we cannot support any profile outside of the outcome of this operator because basically we have a revelation principle, so without loss of generality on the equilibrium path, players need to follow the mediator's recommendation, and given that on the equilibrium path, the equilibrium recommendation history is common knowledge, and individual rationality guarantees that this punishment strategy is the harshest punishment. We cannot push player deviator's contention payoff below her minimax payoff. So that's basically proves the other direction. And the last one is that this perfect monitoring, mediated perfect monitoring is a tight bound in the sense that there exists a repetitive private monitoring which achieves this set as a correlated equilibrium, and actually we need to allow players to communicate by chip talk messages after each period as well. And so basically what we can show is that this mediated perfect monitoring equilibrium payoff set is achievable in equilibrium with no mediator, repetitive perfect monitoring, initial correlation, and one round of each talk in each period. Or equivalently, no mediator, repetitive perfect monitoring, no initial correlation, and one round of each talk in each period, but we need to assume that the game starts from period 0, and we characterize the equilibrium payoff from period 1. Then basically, this initial correlation can be done by the private signal that you can observe from the result of the period 0 game, basically. Then these two are basically equivalent. And the idea to show this part is basically, the idea is that the initial correlation contains all the information that you need to know about what is the recommendation of the history contingent, like a recommendation schedule. But we cannot give the information of the recommendation at the beginning because then you get too much information about what will happen in future. So basically, we use the idea of the cryptography that the information is encoded at the beginning so that the players do not know future recommendations, and then construct a chip talk communication after each period so that that communication decodes the recommendation of the next period. And if you tell a lie, then this communication creates some miscoordination in future, leading to minimaxing the deviator. And so we are considering the sequential equilibrium, so we need to make sure that this punishment can be done in a sequential rational way. And this is a little bit hard proof, but I think I don't have time to talk about. So let me go to the conclusion. So here are like 4 things that we have done for this paper. First, by example, showing that the unmediated repetitive private monitoring can outperform mediated private monitoring, yet there exists a sufficient condition with which the mediated private monitoring is the best monitoring structure. And given that, since we offer the recursive characterization of the equilibrium payoff set in mediated private monitoring, going back to our original question, if this sufficient condition is met, then this recursive characterization of the equilibrium payoff set is an upper bound of the equilibrium payoffs with some monitoring structure with fixed discount factor. And the last claim is sort of saying that this is actually also a tight bound in a sense that there exists a repetitive private monitoring which achieves this E of delta as a correlated equilibrium, or we assume that there is no initial correlation device, but the game started 1 period before. So that's pretty much it. Questions?
Do you have could I maybe look at the 2x2 game or other game where I just change a parameter of the game, of the payoff entry, that eventually I'm going to break or attain that sufficient condition? You know, I don't know, take a prisoner's dilemma, or is it, or?
Yeah. So it's written in probably not the most transparent way to check the sufficient condition. So basically, Wi is equal to 1 over delta divided by delta di plus minimax payoff. So we can consider in a prisoner's dilemma sense, for example, if we change the discount factor and the discount factor is getting 0, then this guy is getting bigger and bigger, because if this is 0, then this guy diverges to the infinity. So we eventually violate the sufficient condition. If we change the payoff of taking defection when the other guy is taking cooperation, for example, there's a maximum deviation gain is getting bigger and bigger. So I guess this guy is getting this, and this guy is getting that, and we will also violate the sufficient condition at some point and things like that. So yeah, we can do the comparative statistics with respect to the primitive of the model, and for that purpose, it's better to write down W lower bar in this way rather than that way. Yeah.
I guess then you would want to maybe relate that to what you give up when you don't have the omniscient mediator, right? So that there's something that you can do more, but when you have the sufficient condition, that more is not needed in some sense.
Right. Yeah, I think yes, as I answer to Ben's question, this E of delta with perfect monitoring mediator thing, the characterization of this guy is always obtained regardless of the sufficient condition. But it's a little bit hard to say that how small this set is compared to the omniscient mediator, because we don't have a good characterization of the omniscient mediator without the sufficient condition. But again, I agree that that's an important and interesting question. So yeah, if we can proceed a little bit further for that direction, then that would be good.